Okay. Good morning, everyone. I welcome you all for this 5-day FTP program on mathematics for machine learning. So in the previous last two sessions, you have heard that machine learning is nothing but a simple black box. So let me enumerate that. Let's say you call this as a black box. You have a black box. And we call this as ML, machine learning. And something which gets into this box and something which is going out of this box. To be precise, what's getting inside this box is your input, and what's getting out is your output. So input would be a set of vectors, and output will also be a set of vectors. So the whole idea about machine learning can be mathematically thought about as a function f that maps some vectors v suffix I stands for input, to some set of vectors v in the output space called O. So it's just a simple notation which tries to make you life more simple. So the whole idea is in this talk is to understand this black box. That means what is input given to this black box and what output it spits out. So let's try to understand vectors and where are these vectors, how do we get these vectors, what are the operations which we do on these vectors. So the first step what we want to understand is what are these vectors. So vectors, before I just talk about the normal definition of a vector, so let's try to understand in a very general sense, right? So in a general sense, if you take up any applications, for example, let's say an application of mobile, let's take up some applications. So if you take up some application, something like mobile, traffic, and then city lights, for example. So all of these would generate a lot of data. I would say a lot of data, or a huge data. So it generates a lot of data. So effectively, if we look at this example of city lights, what essentially we want to do is the number of lights which are there, if you can drop it on the map, you could verify that. You could easily find out the activity based on the distribution of these lights. More the lights, you can say, more the developed countries or the cities they are. But however, we want to still understand a basic question would be how the energy consumption, we want to estimate the energy consumption per city. Why do we want to do this? We want to analyze and come out with a new plan to use that energy sensibly. So this is something which we want to try out. So first one application, that means we are looking at an application of city lights that's generating a lot of data. So this helps us to understand data better so that we can take informed decisions. Similarly, if you look at another example of mobile phones, which is generating a lot of data in the form of images, audio, video, text, we just want to analyze. A basic question would be like how many hours you are spending on the mobile phone effectively. So this would help to find out those who are really addicted to certain applications and what why the certain applications are not being used more, so that you could come out with better informed decisions to create better applications that would help users. So these are certain things that would, these are certain applications, you could think about. Even if you look at a traffic light, the traffic, if you look at a city scenario where it generates a huge amount of traffic. So even in this scenario also, we want to estimate or we want to predict the next, uh, outcome. So we want to check out how much of traffic would expand in a city given the current scenario. So in all of these applications, the main ingredient for all of them is this person called data. So if you look at those data, which is now abundant and huge, what essentially is a data? So a data could be thought of as a point in that space, or it's a vector. So each of those data are nothing but a dot. So if you look at a map, then I can say these are city lights. So if you just look at a map of, let's say something, I'm just trying to fill up these maps by something. So if you look at, these are the lights. These are the lights. Now it's just showing that this continent is maybe it's not so densely populated, but that's fine. But if you look at another area, maybe something like this, I'm just drawing a hypothetical, drawing. It's nothing to do with any continent of our world. So if you just look at, so these are like sparsely connected lights. So sorry. So these lights or these data points which are representing, it could be light, it could be mobile activity, it could be traffic, it could be Facebook, it could be Twitter. You take up anything. So all these could be a part of your data. And now what I'm trying to tell you is this data point which are referred to can be thought of as a vector. Okay, so that's your space, and the vectors, these are different kinds of vectors. So I have one vector here, another vector here, and I have one more vector here. So these vectors are spread out, and I know that these vectors are sparse because they are very few in number. Okay. So with this motivation example, let's try to dive into a detailed way of how we could use these vectors and build a model. So let's say we were looking at a motivating example. So one of the motivating examples would be that you have a black box. So the black box would be some kind of a neural network. Let's say these are my neural network. So I'm just trying just to make sure you understand. Okay. So it's all fully connected. So I'm just trying to fill this. Okay. Okay. So this is your model or your network. So what you get here, all these are inputs, and let's call them as X, and what you get output is a Y. Okay. So that's the goal is to, as we have already discussed, the goal is to just minimize this Y cap. That's your error. Okay. So how do we do it, and what are the things that goes inside are all taught in previous and the next session. So now we want to quickly go into what are these vectors and how these vectors would help, just to with a motivating example. So let's assume that we are trying to form. Let's say that we have a height of a person. Okay, these are height of a person. I'm just trying to draw without any scale. So these are some height of persons. Okay, and then if I just try to fit, if I try to fit something onto this, I would approximately get some kind of, okay, I think I did very badly here. Let me go back again. Okay, so what you get here is the maximum peak, and this can be termed, I mean, if you look at this curve, it looks like some kind of a normal curve or normal distribution. And some of you who are from math background, you will call it as a Gaussian distribution. Okay. So we know that for this curve, we have two parameters, that is your mu, that's your center, and then that's your width. This is given by your standard deviation sigma. So if you assume that this is the height of a person which are measured, and if I take that height of a person is not less than 1.5 meters, and the height of a person cannot be more than 2 meters, and then I can define a Gaussian equation like this. So let's say f of x would be defined as 1 over root 2 pi sigma exponential minus x minus y mu sigma square. Okay. So now you might guess, why did you, how did we fit this line? And so the question which we are asking is, how did you fit this line? Right? So the question is, how did we fit this curve, and is this the best fit? Okay, so this is the question which we are asking. So essentially we are looking at the goodness of the fit. Right? We are fitting some curve and we are trying to find the goodness of fit. So one could argue that, why did you fit? So I might come out with some other where I could reduce the mean, and I would say, okay, let me take up this one, so it might come out with this, and I have a curve which looks a little bit flatter. So what's essentially happening here is I mean, if you look at all of this, so I'm just trying to underestimate here and overestimate here. Right? So these are overestimation. And this is your underestimation. So you might also come out with different variations of sigma and mu, and you would now think that this has two parameters now. If I can show you, the goodness of fit can be represented as a vector. This is what is the essential part. Now I would say G of f of x, goodness of f of x can be represented as a vector of two parameters, mu and sigma. Now this could be represented as a vector. Now essentially we are estimating mu as well as sigma, and now one of them would be, because we are estimating, I'll call them as mu cap and sigma cap. So you might come out with different values of mu cap and sigma cap, right? So mu cap would be a set of values where I would say mu1 cap, mu2 cap, and so on. Let's call them as mu-n cap. And the sigma cap can also be sigma 1, sigma 2, so on up to sigma m. So why I'm differentiating between m and n is because I don't know what values of sigma, it would give me this fit. That is the green color. So we all know that green color is the best fit, and the blue color is not the best fit. So if I try to plot a contour of this, so let me change the color so that it's easy for you to understand. So if I try to represent this with the two parameters, so the two parameters are your mu and sigma, and now if I try to plot, so I might start from here. Let me use a different color. So I might start from here. So this is my initial value mu1, and now I would get a contour plot. So now I would now start changing the contour, the mu and sigma. So I might get a little better than what I already had. So I might get something like this. So again, I just try to do another one. Let's do another one. And I get, right? So, sorry. So now what essentially we are doing is, we started somewhere here, and now we are actually moving from here to this point, let's say, and from here to this point, okay? And this point where you're looking at is my optimal solution. This is my optimal solution. So bear in mind that we never get to optimal solution, we always get to an approximate, right? So this is a form of minimizing the error. So what I'm doing is, so the error here is minimum, this is maximum. The reason is because it's not a best fit. If you look at, I might think about, changing my sigma, I'm just changing only sigma here. It could be change of mu also, where I'm shifting. So I'm just shifting this mu to a new. So this is mu1 cap, right? So essentially, what I'm trying to do here is I'm trying to estimate these, and I'm trying to. So now the whole problem. So I think now you know that the idea is to understand. So if you can understand vectors, okay, and a little bit of calculus here. So this gives you the solution for the problem you're trying to solve. That is your goodness of fit. That is goodness of this function, fitness function. So that's, with this motivating example, let's turn to what are vectors in linear algebra, and then how are these represented, and then we'll move on to the next topic. Right? So vectors, now we know that vectors can be defined in many ways. So let me take, okay. So let's start with vectors. So physically what we do is we just try to write an arrow and say this is R, and sometimes we write arrow here representing vector. It's just a vector. So we all know by physics that a vector has both magnitude, the length of this, and the direction, right? In what direction it is going. So this is one way. Physically, this is represented as, a vector could be represented like this. So from, geometrical point of view, let's say, we have a house. Let's say we have a house, and we could represent, let's try to write some properties of this. So let's say the house is of 120 square meters, right? And then it has 2 bedrooms and 1 bathroom. And let's say the cost is around 150K, right? So let's say, because in India, let's say it's rupees. So now this is a whole lot. So I could now represent this house in terms of some values. Now I can write down this values as 120, 2, 1, and 150. Right, so 150K. Let me just write down. Right, so now this essentially would now be packed up into a vector form, and now this is with respect to physically or geometrically. Physics people would look at vectors like this, which has both magnitude and direction, but nowadays data scientists would now look at something like this. So now, essentially, if you look at this, if you look at this, it's nothing but the array or a list representation. So it's a list representation. So now I know that vectors could be represented physically or geometrically. I could also represent vectors by taking all the properties of those objects, any object, and then put them into a bracket, and then I say in a list representation. So from here we want to move on to what kind of operations I can do on these vectors. So let's try to find out that operations I can do on the vectors. So the first operation I can do on vectors is addition, and the second operation is the scalar multiplication. Okay. So let's try to understand geometrically. Let's try to pick up two vectors, and let's say we want to add them. Let's say we have vector r here, and we have some vector s here. How do we add it? So essentially what we are doing is we are adding s plus r. So what you are doing is you imagine that you're just trying to push this stick virtually, and then you're just dragging this, and you're trying to put this at the end of this. So if I'm right, okay, yeah, I'm just trying to do this here. So what I'm doing here is I'm just trying to push this up here. Now what essentially think that this vector is here, and where that vector lands is actually your addition. So that's your resultant vector. So what you get is nothing but, so this side is r magnitude, this side is s. So this is nothing but r plus s, right? So in a list representation, you could define something like this. So r will, sorry, let's change the color. So r will have two elements. Let's say R1, R2. I'm just doing an abstract way, and we'll do a concrete example. S would have S1, S2. I'm just taking only two components here. Reason is because I'm just thinking in terms of two dimensions. So what is R plus S? R plus S is nothing but component-wise addition. So you take R1 here, add it to S1. You take R2 here, add it to S2. So that's your, a list way or representation of a vector representation of this. This is a graphical way of representation. So this is your vector addition. So how do you do scalar multiple? So let's say you have, let's say you have a vector R. This is a vector R. And I want to multiply this with some scalar, let's say 2 times of r. So now the direction is not changing, but now what you're essentially doing is you're enlarging the vector. So instead of placing here, now position is changed to twice that of r. Now you could also do that by reversing it, and my direction will go down. So maybe this is half r, right? This is where I start. This is half times of r. So I can, so maybe you can half of r, sorry, minus half of r, because it's going in a reverse direction. So now with these two operations, it's clear that I can generate any combinations of vectors using these two rules. So using these two operations, addition and scalar multiplication, I can generate a third vector. So how is that? It could be something like this. You have 2 times of r plus s. So what you get here, let's say r is this. So r would be 2 times of r. So you get 2 times of r1, 2 times of r2, plus s1 plus s2. So what you get is a new vector, right? So this position of these vectors would now maybe, if I just write it here, or maybe it would go something like this, right? Now with certain, if I take all these vectors, right, let's say this is my vector r, and let's say this is my vector s. And now if I take all the combinations, so if I take all combinations of r and s, okay, then you would now see that, it fills up the entire space. It fills up the space, right? It fills up this space. It fills up this entire space. So now what you see here is called the span or of these two vectors r and s. So I would say that these are, the set of vectors, span or set of vectors that fills the space. Okay. So in this case, the space is 2-dimension. But if you look at in case of 3-dimension, then it would span 3 dimensions. Something like it would now fill up it would take up in x way, it would take up the y way and the z way. So now what I get would now be, okay, I think I just, right. So if I just take only this plane, okay, if I take only this plane out, now it would be a plane, just a plane, right? So there are some vectors here, but now these vectors are represented in terms of x, y, and z. There are 3. So this will be in terms of 3 dimensions, right? So now we have come up to a point where that we know that we are looking at the linear combinations of vectors, and these linear combinations of vectors would fill up our entire space. So this will help us in trying to understand, how can we fill up them? Do we need all these vectors? So let's say if I'm taking this example, so do we need all the vectors here? Let me enumerate it. Let's say V has V1, V2, all the way up to Vn. So do we need all these n vectors, or do we need only a small subset of vectors? So that's the catch. So the whole point is we need only small subset of vectors, which could, by doing these operations, which could help us in trying to get all the other combinations. That means, so these set of vectors are called basis vectors. They are called basis vectors. we'll try to study it in a couple of minutes from now. So these are called basis vectors. The reason why we are calling it as a basis vector is because using these two vectors, I should be able to fill up the entire plane or entire space in 2 dimensions or 3 dimensions. So if you look at 2D case, I just need only 2 vectors. That's called I hat and j hat. So you all know what is I hat and j hat. These are all unit vectors. I hat and j hat is a unit vector. I just need only these 2 vectors. So these 2 vectors, essentially I hat and j hat vectors, are called, they have a special name called independent vectors. They are independent vectors. Now these are only 2 independent vectors, and using the linear combinations, you know what are linear combinations? Using linear combinations of I hat and j hat, we can fill up the entire space. Okay, so those are called as the independent vectors. So we now have come to a point where we have understood. Let's try to recap. Let's try to recap what we have done so far. So what we have looked at, the first step is we looked at data as points in space, as a point in space, in a space. Okay, the space is, so the dimension of this space is not defined right now. Let's not bother too much, and it will get cleared. So don't worry too much. It's okay if you don't know what is the dimension of the space. Let's assume that there is some dimension for the space right now, and there is one point or a dot in that space, and that is nothing but your data. And now, we said that these data is nothing but vectors in that space. And we looked at a big picture. We looked at big picture, how to construct a model. That means we looked at this big picture that we had. I'm just trying to redraw it again, that this is your black box. These were set of vectors. These were some set of output vectors. So these are your V in and V out. These are set of vectors which are input and output. And we said that these vectors, the operations which we can do on these vectors, which are very simple, that we can perform addition. We can perform addition, and also we can perform scalar multiple. We can also perform scalar multiple, and using these 2 operations, I can construct any vector. I can construct any vector. Okay, I will say construct. I would be able to construct any vectors through, and these vectors are nothing but the linear combinations. So when I say linear combinations, they are nothing but they are dependent on one of the vectors. So it's as good as saying the first vector is 2, 3. For example, the first vector is 2, 3, and the second vector is nothing but 4 and 9. Then I would now say, let's say this is V1, this is V2. Now, if you think about these 2 vectors, V1 and V2, I would say V1, V2 is nothing but square of V1, right? So that means it's dependent. So if I know this, if I can get this, and now what will happen is this V1 will now become the independent vector. So this is very essential for your help to map your machine learning terminologies, right? If you want to understand machine learning, we want to have only a few vectors that could essentially are trying to reduce the dimension. We don't want dependencies. and then we don't want to feed those dependencies to a machine so that it tries to mug up. It's something like a rote learning. You're trying to show the same kind of vectors in a different form. So that would not help a machine to analyze. So it is just like a memorization. So we don't want the memorization. We want a machine to generalize well. So therefore, we want to avoid this. So the first step is to try to understand why this dependency and independency plays an important role. And then we want to look at the data, then try to eliminate this. So that's the the next step. So that your machine learning model would help you to. You'd be able to define and design a very good model for that, right? So these are you also saw some of the representations of these vectors. You also saw, let's say, let's call it as 5. So we saw some representations of vectors. Right. So we also saw some representation of vectors. So representation of vectors could be geometrical. Geometrical in the sense I just have to have one arrow. You also can it can also be represented as some abstract way. In a very abstract way, I can take any vector and then represent it as collect everything and put it onto a box. And it can also be represented as a list way, in a list representation. So we saw all of them, and then so in the next topic we will try to cover few more things about what is vector space, how this spanning of I just want to move from this idea about getting onto a small space and then moving on to a higher dimensional space, and what does it mean for these vector spaces, and how do you find the basis vector, what is the intuition about vector space. And then we will try to understand now what we have done is we have just seen only with respect to vectors. So in the next we want to look at the motivating example for matrices, and then we'll try to cover some linear transformations of these matrices, and that should be able to help you out to appreciate the concepts of linear algebra, which plays an important role in the building of machine learning applications. Okay, welcome back. Let me know if you have any doubts. You can put it in the chat box, or we could discuss it offline whenever you have time. So let's start with vector spaces. So essentially, what is a vector space? It's nothing but set of vectors. If you look at it's nothing but set of vectors. Now, how do you get the set of vectors? Through some linear combination. So we all saw that you have two vectors. You have two vectors R, and you have another vector S. And if you try to add up these two vectors, so I would now get a parallelogram. So you would end up here. So this is R plus S, right? So similarly, if I have another vector here, somewhere here, this is maybe a P, and I would add it with S, then I would get to here. So P plus S. Okay. So if I just go on doing it for all of them, we all said that it now fills up my entire space. So this would now be treated as some dots. So these dots are nothing but vectors in that space. So I'm just trying to recap what I told you in the earlier session. So these vectors, so these dots represent vectors in 2D space. So now let's look at the dimensions of these vectors. Sorry, dimension of the space. So this dimension of the space depends on the, so if I want to define what is the dimension, I would say the dimension of this space. Now it all depends on the dimension of a space. The dimension of a space is nothing but the number of independent vectors. Okay, the number of independent vectors. So you all know in a two-dimension you have only, if you're considering two dimensions, then we have two independent vectors I hat and j hat. So therefore the dimension is 2. Now if you're looking at 3 dimensions, so now I have I hat, j hat and k hat. So this is my I, j and k. So therefore now my dimension is dimension of the space that it spans all of them. If you take a linear combination of all of them, then it will become my 3D space. Now in general, if you are looking at in an n-dimensional space, which is very hard to write, so in general, so the dimension of n-dimensional space is nothing but the number of independent vectors it has. Independent vectors. Fine. So if you have n independent vectors, so it will be in an n-dimensional space. So if you have less than n independent vectors, then I would have a k-dimensional space. Fine. So now we turn back our attention to what is basis. We all know, let's try to define the basis vector. So we all know that vectors that are not linear combinations. So basis vector definition is that vectors that are not a linear combination. That means they are independent vectors, right? And they span the entire space. Fine. So let's take some example and then make your make it more clear. So let's say we have some vector b1. Let's say we have some vector b1. Let's call it as b1. We have some vector b1, and then any scalar multiple of that. Right? Any scalar multiple of that. So that means if you take any scalar multiple of that, that would lie in this this plane, in this line only, right? So any linear. So this, let's say this would be 2 times of b1. Somewhere here it could be 3 times of b1. So somewhere here it would be minus b1, and here would be minus 2 times of b1, so on, right? So if you take let's say if you have some vectors, and a scalar multiple that the span that means it has only 1 degree of freedom. That means it can go in only one direction, either in the positive direction or in the negative direction, right? So similarly, if I have 2 vectors, another vector, okay, let's call it as let's take the same thing. Let's say b1. And let's say we have b2, another vector called b2. Now the span it makes, that means I have 2 degree of freedom. That is, any linear combination of that would fill up this space, right? This whole entire 2-dimensional space. Is it clear? So this would span the entire b1. This would span the entire b2. So internally together they form a linear combination that would fill up my entire space of 2 dimensions. So similarly, if I have another vector b3, now it spans the entire a cube. So independency is defined as, that means B3 should not be equal to some linear combination, that is constant times of B1 scalar multiple of B1 plus some scalar multiple of B2. So if you can understand, so such vector B3 is called as the independent vector. So this is defined as your independent vector, and in other words, they are called bases. That means they are the fundamental vectors. Otherwise, it becomes a dependent vector, right? I hope you are able to understand this. Okay, so let's try to define some intuition of independent vectors and then go ahead. Okay, let me change the color. So what are basis vectors? So I'm just trying to define few things. Basis vectors, okay, basis vector, some points, they not necessarily be first one, a unit vector. It need not be a unit vector. Okay, the basis vector need not be a unit vector, and it also says that it not necessarily be orthogonal. Okay, let's try to this orthogonality, and this will be dealt in the second half of this session. But I just want to make this point clear that if you have orthogonal vectors, then it is easy for us to work on, right? So what do you mean by orthogonal vector? Just to be sure, just to fill up this space. Orthogonal vectors are if you take the angle between these two vectors. So until now, what we have done is we have said that we have two vectors R and we have another vector S. We have not defined any measurement for this, something like what is R, what is S, the length of R, and then the angle which goes into this R, right? So theta. So it says that the angle between any two vectors, if it is 90 degrees, then they are called orthogonal vectors, right? So let's not do it right now, but what we want to do is we want to understand these things in a easy way. So until now, we know that the basis vector need not be unit vectors and they need not be orthogonal vectors, right? So now now my question is, what if the whole question is, what if the basis vector, right, if the basis vector is not orthogonal, right? So we all assume that if it's orthogonal, then it's easy for us to work. But if it's not orthogonal, then we can't simply use the vectors, right? If it's not orthogonal, then we can't use vectors. We cannot use vectors. But what's the solution? The solution is we need to go from vectors to matrices. So this matrices would help us to define. So till now we were looking at what are we looked at vectors, the combinations of those vectors with a scalar, and then adding up those vectors we got a linear combination of, and then we said that these linear combination would fill up the entire space, whether it's a 2D or a ND. And now we are saying that if the basis vector, we also looked at what are the basis vector. That means the vector which you are defining should not be a linear combinations of any two vectors. So we said that if the basis vector are orthogonal, then it's easy for me to do the manipulation. So suppose if my basis vectors are not orthogonal, then I cannot use simple vectors. I have to use an idea of matrices. Now I have to look at what are matrices, And let's try to define matrices as a linear transformation of vectors. So I just want to put it in this way. Matrices or matrix is nothing but linear transformation of vectors. So we all know what is linear because we are looking at degree is 1, but this is a fancy way of saying that it's just a function that maps a set of vectors to another set of vectors. So let's try to look at some motivating example and then see what's the linear transformation of that. Let's say that we have a vector. Let's try to define our I hat. So that's my I hat. Okay, that's my j hat. Okay, so that's my two orthogonal, or I would say these are two normal. They are normalized vectors or unit vectors. Yes, and now I define another vector. Let's say I define another vector v. Okay, and let's try to give it as 1, 2. Let's say this is 1, 2, right? Now what I want to do is I just want to flip this, in the sense I just want to change this I hat. So I just want to change a little bit and then say I want to do some, this is called a transformation. So that is your T. So I want to transform. I don't want, this is in the I hat and j hat space. Now I want to move this vector v to some other, some other place. So let's try to define it. Let's use a different color. So let's use white. Okay. So now what happens is, now I hat would now come here. So let's say my transformation vector, that is, I just want I hat to move in -1 and 2. I just want to move I hat. I just want to move I hat with -1 and 2. So here this I hat moves here, and this is my new I hat. Okay, so my new I hat will be -1 and 2. Okay, and let's say I just want to change my j hat to, let's say, 3, 0. That means I want to move this I hat somewhere here, j hat somewhere here, with these two new coordinates, and I want to see where this v lands up again. So so this would be, let's say, I just draw it. This is my j hat, new j hat, which lands up at 3, 0. So what will happen to my new vector v? My new vector v would now end up in somewhere here, and we want to look at what are its coordinates, right? What are its coordinates? So this can be done by using a scalar multiple. So that means, how do I do it? How do I know that where this v hand lands up in the new transform space? So that could be written as -1 times of, this is a -1 times of this vector 1, 2, -1 times of this vector 1 and 2, 1, oh sorry, this is -2 here. Okay, -1 times of vector 1 minus 2, and then let's say 2 times, I'm just taking this -1 times of this, and this is 2 times of, this is -1 times of 1 minus 2, and 2 times of 3 and 0. So this would end up in 5 and 2. Okay, so this is nothing but 5, 2. Right. So how can we? This looks little bit a little bit of math manipulations, but can we do it better? Can we do a little bit better? So if we can, if we know where I hat and j hat lands, right? Then we could construct a matrix and then try to multiply that with a vector and then come out with the answer. So in a simple term, so I would just say that this could be my transformation matrix T would now be, I know where I hat and j hat lands. So I hat lands at 1 minus 2, right? And my j hat, right, I'll just try. My j hat lands at 3, 0. Right, so this could be easily packed up, and what you have here is where the I hat lands and where the j hat lands, right? And now I can just try to multiply this with a given vector, right? So this is my transformation matrix, right? So now I can just just give my it's nothing but the linear transformation of that, and now I can just multiply with the vector which was there in this. It's 1 minus 2. Yeah. So I'll just give some vector 1 minus 2, and then you could get a vector space. You could get a new vector. So this is where the vector which lands in the transform space. Okay. So maybe a concrete example would help. So let's say if I take 1, 3, 2, and 0, and let's try with let's say 5, and let's call it as 7, because I've already done this calculation and I don't want to do it, so it will be easy for me. So this would be 26 times of minus 26 and minus 10. So now I can use this as a transformation matrix just to make sure where my I hat and j hat lands, right? So now what we have done is we have seen we have seen matrix as a linear transformation. So you can look at matrix even in algebraic form, matrix in the algebraic way. With algebraic approach. So let's say I go to a shop and I say that I buy 3 apples, and let's say I buy 4 bananas and it costs me around 12 rupees. And on a round trip, I just buy 4 apples and 2 bananas, and it just costs me around 8 rupees. And I am interested to know what is the cost of an apple and banana, cost of an apple and a banana. So we all know that this could be written, this is kind of simultaneous equation where you try to solve it and get the answer. But in another way, we could write down this as a coefficient of this as a matrix. That is your 3 and 4. These are coefficients of A and B. Then you have 4 and 2. This gets multiplied with the unknown. That is your A and B. And I'm interested to look at this 12 and 8 is my solution. So I'm trying to ask you, if you solve it, because I've already done it, I'm just going to show you that A would be 0.8 and the apple for a banana would be 2.4. So, what you could do is you could solve this. So how does this help in machine learning? So basically what we are looking at in machine learning was, again, I just want to throw you your attention on this. So it was your black box. You had some vectors. We looked at these vectors, set of vectors. Now you had output. So you have in and out. And now these vectors, we said that because they are not, we also understood that at some point of time vectors are not useful, and we need to go to matrices. And these are your matrices. Some matrix, we are looking at in this form. There's some vector multiplied, so it's a dot product. We are multiplying a matrix with the vectors to get me a vector. So I get the vector. So I am calling this in terms of machine learning, these are feature vectors. This is my weights, and these are my predictions. So if you can remember what we said, the feature vectors was X. This is the weight, which you learn a little bit from now, and this is my Y cap. Now what essentially I'm doing is, I know these features, right? From F1 to Fn, I have n set of features, and I define some weights for each of these in terms of neural network, which I think Nagushan sir has already talked about. And finally, what we get is, the class label C1, C2 to, let's say, finite number of classes, let's say Cn. So there are n number of classes. So the whole idea is, I really have no idea about what each feature weightage is. So by tuning, I am trying, by iteratively, I am trying to find the error and trying to minimize, and whatever I'm trying to update is nothing but this weight. So I'm trying to use this as a transformation matrix, and in the machine learning terminologies, if I can spend some few minutes now. So it's nothing but you're trying to use this weight as a transformation matrix. And I know that, so the whole essence of linear algebra is this, that you have some matrix, you have a matrix, right? You have some matrix as a transformation of vectors. You have some vectors, you do some operations on these vectors. And okay, let me draw it. I think it will be clear for you. So this is my space. Okay. I'm just looking at two-dimensional space, and I assume that these two are my vectors. These two are my vectors which I'm taking. I'm just taking only a few examples. So if you do any linear combination of these two vectors, right? So if you do addition or subtraction of these two vectors, so the solution should also be, that means the vector should end up somewhere here, right? So my solution vector should end up here, right? It should end up here. What if my solution vectors end up out of my space, right? So this is some other space. This is my space, and this is a different space. I will not have any solution. So the whole idea about linear algebra is, this would now be approximation now. In later course, you will see how can we solve this problem using whatever you have learned in your math. That's also called as the least square approximation. I think you have learned this, and even in the first few sessions of vector calculus, you have learned this, the idea about least square approximation. So the whole essence of least square approximation is simple. I have a vector x, I have a vector y, I do some operations, and I end up in a space which is outside this solution space. So that means I can't figure out, I don't have a solution. So that means there is a solution, but I can't see that solution. So therefore, I need to approximate it by somehow, I need to approximate, approximation in the sense I'm trying to cast a shadow, and they use projection and things like that we will cover up in the next sessions to come. But right now, you try to understand in a very basic nutshell that this is what we want. But in a very general case, you would get this scenario. That means you have these vectors as a transformation matrix. You put those vectors in a transformation matrix. You try to apply it to your feature vectors, and now you see that I don't get a solution. Why? Because error is more. Because the error is more, you don't get exactly what you want. You get something different. Now, how do I match with this? Is to minimize that error by doing a back propagation. Right? So I hope you know these transformation matrix, And there are different kinds of transformation matrix which are available. I don't want to deal with this right now, but in a very simple way, transformation matrix would be trying to transform from one, you're changing the directions, you're changing the alignment of one vector which was originally there, and you're trying to move it across. So how is it useful in machine learning approach? In the machine learning approach, you iterate over these vectors as a linear transformation to map these vectors x correctly to the vector y. So what is vector x? So vector x is your input features, vector y is your actual output. So you mean to say that these are my features to represent a cat, and I know that this would definitely end up in saying that it's a cat and not a dog. Even if there is a slight variations in that, right? So I hope you know that, and the whole essence of this is to minimize these errors. So let's try to I have just one more just one more topic until we close this session for now. So let's try to see what's composition of these vectors. So this is seriously important. Composition of matrices. See, when I say matrices, just think of matrices as a linear transformation of vectors. Okay. Now, I just want to give you one example how this could be useful for your, in designing your machine learning model. So, what is compositions? We all know what is a composition of a function. You try to compose one, function to another function. You get a different kind of function. So here also we are trying to compose transformation matrices to get a different different matrix. So let's see what are those. So ideally I just want to draw a neural network here. Let's take 3 input. So these are my inputs. So this is my x1 here, this is my x2 here, and this is my x3 here. So these are my input vectors. And let's say I have, this because it's, don't worry, I'm just trying to draw a layer which is hidden. So if you don't understand this, it's okay. But it's just a model. We don't want to stress more on this. Okay, I'm just let's try to fill this. So you have just goes to everything from here to here. Sorry about my drawing. Okay, so 1, 2, and 3, and the last one. Yep. So now what's really happening is let's assume that this is my input. Okay, this is terminology. This is my input. I some layer in between here. Let's call this as hidden H1, and let's call this as hidden 2. And let's call this as output O. Okay. So now what you get out is a hypothesis H of X. Okay. So let's try to understand this a little bit. So now what's really happening is we have some weights which are associated with these, as I was talking to you, and let's try to define this as a weight vector. So let's say what's H of W weights of H1, that's defined as W11, W12, W13, let's say W21, W22, W23, because it's a 3 cross 3, 3, 2, and W33. So this is my 3 cross 3, this is my transformation weight matrix. How did I get these vectors W11? So this is with respect to 1, 2, and 3. Right? This is 1, 1, 1, 2, 1, 3. Right? Right? I hope you got it. Right? So let me just write for 1 because it just gets clumsy. So this is 1, 1. So that means this is from input 1, hidden layer 1. So this is your 1, 2, and this is your 1, 3. Hopefully the rest of them. So the whole point is trying to understand this one and I'm trying to dot this with the transformation matrix with the vector. So that is your features x1, x2, and x3. And what you get here is the hidden h11, h12, and h13. So that's your intermediate output, right? So I guess, if you do your matrix multiplication correctly, and then I think if you do this transpose, and I think you should be able to get this. So that's not, that's something which we can look at. So what we got now is we got the weights which are associated with this. So let's try to calculate the weights associated with this now, H2. Now what we did now is we had a function that actually took a matrix and f of x. So it's just f of x just gave me this. Now I have another layer which takes this one and gets me to the output. So that's WH2, right? So that's your W11, W12, right? W1, 21, W22, and W31, W32. So I hope you got it, like what we are trying to say. So this transform, you're trying to, just a transpose, sorry, this is not a transform, this is a transpose, and I'm trying to put this H11, H12, H13, and the output which you get is H21 and H22. Fine. So what you're done is you have what you have done is you have composed matrices to get to the output. Fine. So the whole takeaway is this. So what's the takeaway? So why are we doing this? So how does maths play an important role? So now you can be sure, and you can now appreciate that inside the hood, under the hood of any neural network, or people call it as a black box, is nothing but some kind of a dot product or matrix multiplication. So under the hood of every neural network, it's nothing but function composition. So what's really happening is it's nothing but a function composition. Function composition. sorry. Excuse me. So what's essentially happening is, so you try to compose two linear, fine. So I have two linear function which will do this way, and I have a linear function which will do this. So if I do a composition of this together, I would get something like this. May not be an actual curve, but I would get something like this. So now what I did is I created I composed two linear functions to get me a nonlinear function. Okay, so I hope you have learned what is activation function and things like that. So therefore I'm not stressing more on that. So mathematically speaking, composition of transformation matrix is nothing but mathematically what you're doing is you're trying to compose two matrices, that is let's say A2 of A1 of R. Okay, R is just a vector. Now what I'm doing is I'm trying to do a dot product. First I do A1 with R, and then whatever the results I get is again a vector, and then I just try to do a dot product with A2, and finally I would get another vector. So this way I am trying to compose different linear functions to find the curve fitting. So ultimately all your machine learning algorithm is simple. What essentially it's doing is it has even if you're looked at in terms of your linear regression, so what you're looking at is you have some set of points here, you have some set of points here, here class 1, you have some set of points here, these are class 2, and your classification algorithm essentially is doing what? It's just trying to fit a linear decision boundary to separate out between this class and this class. So this is a clear case of linear separable. Suppose if it's not linearly separable, something like this. So if you have this way, okay, so then you need to compose many such many such layers to define a decision boundary, and what I get is something which is approximately like this. So this can be achieved by composing many different layers. So that's the whole concept about moving from one layer, a single layer perceptron, to a multi-layer perceptron, or sorry, multiple layer perceptron, and that's the simple example which you can think of as a deep learning. So in deep learning, what we have is nothing but like this. So that's your deep learning. So I'm adding multiple layers here, and I'm making sure that whatever features are learned here, you try to make sure that you tend to give it to these many layers, and each of those layers are trying to handle a particular feature, and we are trying to tune those parameters to get to a final answer. So with this background, we will stop here, and we will continue next. So I just want to give you a preamble. So that means we have seen only vectors here. We haven't looked at any coordinate system for these vectors. We have just seen vectors irrespective of these coordinate system. We have just seen only addition and multiplication, or scalar multiplication. We haven't done any measurement for these vectors like length and dot product. So based on these two, we should be able to define a dot product. And once we know the dot product, this would help us to define our the projections, and using these projections we will try to answer the question which we struggled, that what if the solution vector is out of my space. Okay, so thank you very much. We'll all meet in the next session.